So yes, classic NMR, crystallization and beyond. So first of all, I guess I better tell you what I'm going to talk about. So just explain quickly what classic NMR is, what the technique is, and then I'm going to look at 4 different applications that we've done over the last few years, most of which, but not all, have been done here on the 850. So what does classic NMR stand for? It's combined liquid and solid state in situ crystallization NMR. And so obviously we were using it in the first instance to study crystallization. And when we first came up with this idea, it was very simple. We do cross-polarization on carbon or phosphorus to look at the solid phase as it was crystallizing, but at the same time, effectively, we'd use direct excitation on the liquid phase so that we get information about the species going out of the liquid. And so this is the kind of data that we can get using that basic technique. This is looking at menthol. And here you've got on the left the direct excitation spectra, where you see the liquid phase in the first few minutes. And then quite abruptly, it changes. We get no more liquid signal, and we start to get a solid signal. And in this particular case, we see 2 different solid phases. We first of all see a broad amorphous peaks, and then it crystallizes about here to produce this crystalline menthol. And this was actually the first time that this amorphous form of menthol had been observed. So it's a very powerful technique that tells a lot about crystallizations. There we were doing just 2 different forms of spectroscopy, CP and direct excitation, in order to see each phase. But of course, we aren't just limited to doing A, B, A, B, A, B. We can interleave more different types of spectroscopy and then repeat a larger block of acquisitions to give us more information. And so typically now we would not only look at maybe carbon CP and carbon in the liquid, we'd also look at proton in the liquid, because sometimes that can give us a lot more information than the carbon can. And so this is a schematic of what we would now typically do. We'd have 3 different types of spectroscopy, which is labeled 1, 2, and 3. So 3 different spectra. And then we just repeat those acquisitions over and over again, and then very simply extract the data in order to give us our time-resolved spectra of the different types. And although it's not actually simultaneous acquisition, it's as near as you can get to it, unless you want to do something like SASI, which is rather limited because you're only looking at a single nucleus. So SASI is truly simultaneous. Classic NMR is almost simultaneous, but it gives you more flexibility because you can look at multiple nuclei. So the first thing that I want to talk about today is, as I say, moving beyond crystallization, and this is looking at the formation of a molecular organic framework, a MOF. This is the MOF that we're studying in collaboration with Tim Eason's group, who's now in Birmingham, and we've got our linker molecule. Where are we? We've got our linker molecule here. It reacts with nickel nitrate and produces, there's the nickel there in the middle, and produces this MOF. And to study this, we didn't look at carbon, rather we looked at the phosphorus in these phosphoric acids on the linker, because obviously phosphorus, it's a nice nucleus, 100% natural abundant. So we looked at proton direct excitation to see the species in solution, phosphorus direct excitation again for the solution, and we looked at that without decoupling and with proton decoupling. And the hope was that we'd be able to see the liquid signals if we didn't have the proton decoupling, and we'd be able to see the solid signal if we did have the proton decoupling. CP on this material wasn't working well, probably because the particles are simply too small. And we did this at 5 different temperatures from 60 up to 100 degrees. Now, just to quickly run through the information we got from the 3 different types of spectra. The phosphorus spectra without proton decoupling do indeed show the liquid state signal of the linker, but all we really see is one peak which diminishes over time. We don't get any great insight there. And unfortunately, the phosphorus spectra with proton decoupling, they do just about show the solid state signal, but it's very broad and it's very weak. And again, that's probably because the particles that we're producing are very small, and so they're tumbling too fast to see clear phosphorus signal. But the proton spectra, showing us the liquid state, that's a different story. That gives a number of different peaks, which we can assign to different parts of the linker and to the other components. And what that allows us to do is to see how the reactants are being consumed during the reaction to produce this MOF. So this is an animation of the data which we acquired at 80 degrees C. And what you can see here are signals from all of the exchangeable protons here. So that's the acid and the water and everything that's coming off the nickel nitrate. But over here, we've got the signals from the linker itself. I'll just let that run again. And you can see that they start large and then drop down over time. And they also change their chemical shift. But the important thing there is that we can see their intensity. So what we can do is we can take spectra like this and we can extract the intensities of all of those proton peaks. So we've got 3 different environments in our linker labeled in different colors. And at 60 degrees C, this is the data that we get. We've got basically a plateau. There's a bit of noise in there, but basically you've got a plateau. And then the crystallization, the reaction begins, and we get that drop in intensity as the solution state linker is used up to form the MOF. And so we can then fit that using a Gualtieri model, which includes information about both nucleation and growth of the MOF. And from the information about nucleation, we can get this kind of plot, which shows the probability distribution for nucleation at different temperatures. So at each of the 5 temperatures that we've run, we can see the probability of the nucleation occurring. Much shorter at the higher temperatures and much longer, up to about an average of about 11 hours at the lowest temperature that we studied. So that's a very nice piece of information that you can get out of this modeling. But you can also get the rate constants for both nucleation and growth. And so we can go back to undergraduate kinetics and we can do an Arrhenius plot. And if we do that, we can then extract out activation energies for both nucleation and growth. So just from those series of spectra that we acquired, we can get all the way through to doing a kinetic analysis of the growth of this MOF. And those numbers, 60-odd, 70-odd kilojoules per mole, are exactly the kind of values that are expected from other techniques. So this is really telling us a very nice, complete story about the MOF formation. So the next topic that I want to look at is something that my group, I work with Kenneth Harris. This is something that Ken's been looking at for a very long time, urea inclusion compounds. And in particular, one of the interesting properties that these materials have is that they can exchange a guest molecule that's sitting within a rigid host structure. So this is a sketch of what a urea inclusion compound looks like. You've got this urea cage here, these hexagonal cages. It's actually a spiral going into the board. And then keeping the tunnels open are these long chain molecules. In this particular case, this is a disubstituted alkane. You've got bromines at either end. But because the faces of these crystals are open, it's possible for guests to move in and out of the tunnels. And so if you have a guest which is more favorable as a liquid outside of your crystal, then that can replace the guest that's inside the crystal. And so we could go, in this case, from a dibromo compound to a pure alkane. And if the alkane is longer, then there's a good chance that it will be more favorable and will replace the shorter guest. So the first thing we do is we prepare in the lab crystals, in this case with 1,8 dibromooctane as the guest. And what we then do is we then put those crystals inside the rotor and add some, in this case, tetradecane, which is a longer guest, which is more favorable and is going to, we expect, replace the 1,8 dibromooctane. So as I say, tetradecane is known to be more favorable, and so we would expect that to replace the dibromooctane. So these are the kind of spectra that we get. These are CP spectra. So we're looking here at the solid component rather than liquid. We've also interleaved liquid state spectra, which I'll show you in a moment. But from these spectra, we can pull out the different components. And in particular, we can see, for instance, this peak here at about 26 ppm is growing, and that's because that's the CH2 next to the methyl group in the tetradecane. So that's going into the tunnel structure, whereas some of the other peaks are diminishing over time because they're from the dibromo compound. One thing to mention, this peak over here at 164 ppm, that's from the urea host structure, and that's essentially unchanged throughout the entire experiment. So at no point is the host structure becoming degraded. These materials only maintain their integrity as long as there's a guest inside the tunnels. They will collapse otherwise. So it's important just as a check to make sure that the urea isn't changing, and in this case it's not. So these are 2D spectra that we've put together from our alternating CP and direct excitation experiments. And you can see I've labeled up most of the resonances that we can see from the dibromo and from the alkane. And in the liquid state, we can also see here, here's the alkane disappearing from the liquid over time. So we get a lot of information out of this experiment about how the changes are occurring both in the solid state and in the liquid state. I should say this spectrum is particularly complicated because the tunnels, the molecules are quite mobile, and you actually see quite a lot of signal in the direct excitation spectra as well from those molecules. So we can take our CP spectrum, we can fit all of the data, and we can get integrals of the intensities for the different peaks within the initial guess, which is the dibromo-octane, and the new guess, the tetradecane. Now, it's clear that we didn't catch the very beginning of the exchange process. It takes a few minutes to get from the lab to the spectrometer, and by the time we got there, we've already seen quite a bit of exchange starting to occur. So although I'm showing it as time 0 there, that's really about 10 minutes into the process, and obviously quite a lot's changed. Nevertheless, we can still see growth of the inclusion of the new guest, and we can see a drop away of the initial guess. So we are at least catching, if you like, the middle part of the process. And although it's hard to be sure, it does look like this is pretty much plateaued here. There's maybe a little bit of a rise still going on there. Now, obviously, we're looking at this under magic angle spinning. And so it's a very fair question to ask, how does it compare to ex situ experiments where we just have it sitting on the bench and let the guests exchange without any centripetal force or anything like that? And what we find is that it does seem to be occurring more quickly in the rotor than on the bench. Now, as I say, it's hard to be sure looking at those spectra whether it really has stopped growing. But what we can do much longer timescale ex situ experiments, literally over weeks, and there we see we do still get a slow, steady rise in the replacement of the old guest with the new. So we may be shooting ourselves in the foot a little bit there by stopping when it looks fairly flat, when in fact, if we had the time, we'd be able to carry on seeing it growing more. But it does look like it is quicker under magic angle spinning, and that's something that we'll have to look at more carefully. So as I say, that might be a consequence of the pressure that's generated by the magic angle spinning. That's something, a topic that I'm going to come back to in a moment. Because what we want to understand is, what effect does magic angle spinning have on crystallization? It's all well and good us saying we're studying crystallization in situ, but are we disturbing the process of crystallization by applying this magic angle spinning? So can spinning alter the crystallization process? That's really what we want to understand. Well, the first thing to say is that the kind of pressures that we generate don't get anywhere close to the pressures that are typically required in order to transform one organic polymorph into what we would term a high pressure polymorph. Typically, you need at least 5,000 atmospheres to even start to get into the kind of regime where you might see a new crystalline form appearing purely by applying pressure. So we're nowhere near that kind of range. We're typically working at 50, maybe 100 atmospheres at the maximum. I'll talk more about the range in a moment. So we're not in the range where we'd expect to see completely new polymorphs. But we do know of at least one example, going back to 2005, where the product of a reaction, in this case a dehydration, was different under magic angle spinning compared to what you get in the lab. And that's something that I'm going to talk a little bit more about, because we've gone back to look at that again more recently on the 850. So this is how we need to think about the effect of spinning. We've got our rotor there spinning at some frequency, and inside the rotor, typically, we don't have a completely filled space. Once you start to spin a rotor, and most of you will have seen this, I'm sure, you'll find there's a little void down the middle of the rotor, because as soon as you actually spin it, it all is forced out to the side by the centripetal force, and you're left with a small void. And so the pressure only starts to build at the surface, the inner surface of that void. So the pressure here, right on that inner surface, is basically atmospheric pressure. But then it builds, and it builds according to this equation with the square of the spinning frequency and the square of the distance from the center r. But you have to allow for the fact that you don't get any build-up from this void in the middle here. So you can see here, this is just modeling for water, spinning at 12 kilohertz with a 1.5 millimeter radius and a 0.5 millimeter central void. And we get up to about 60 atmospheres there. So as I say, nowhere near the kind of pressure that you'd need for a completely high pressure form of any organic material. So we've been aware of this for quite a long time, of course, and so we've always kept an eye out for it. We've usually run at least one experiment of different spinning speed just to see if we get something fundamentally different happening. And generally, we don't. Most of the systems that we've studied, we're only working at speeds up to about 12 kilohertz. So we're not in the realms of doing sort of 150 kilohertz. But on that kind of range of spinning speeds, we're not seeing an effect in most of the systems that we've studied. But there is one system which I want to talk to you about where the kinetics of a crystallization are affected. So the product is the same regardless of how fast you spin, but the time it takes for the crystallization to happen is markedly affected. And this is the co-crystallization of benzoic acid and pentafluorobenzoic acid. And we can follow that not by looking at the solid state spectrum, because that's not all that informative, but we can look at the proton signal in the liquid. And so we can see, as I'll show you in a moment, we can see when crystallization happens by the drop in signal from the liquid component. So this is what we see. Two-dimensional data sets acquired at different spinning speeds, and this is just proton NMR looking at the liquid signal from these two acids. On the left, we've got 12 kilohertz, and on the right, we've got 7.5 kilohertz. And in both cases, you can see we've got a little bit of a change at the bottom here. That's just the temperature settling. But then we've got an induction time where basically nothing happens, and then a sudden crystallization here and here. And within 1 or 2 scans, the crystallization is done. So it's a very, very fast crystallization after a long lag time. But look at the time scales. At 12 kilohertz, crystallization happened at about 32 minutes. At 7.5 kilohertz, it happened at about 8.5 hours. So we've got a drastic change here in the duration of this lag time before crystallization happens. Now, obviously, this is just 2 experiments. It's the identical sample, just cycling the temperature and changing the spinning speed. And we are allowing for the different effects of the heating from the spinning on the temperature. So we've taken that into account. So these are identical temperatures inside the rotor. That's just 2 experiments. It's a stochastic process, so we can't read too much into just 2 experiments. So we did some repetition. Don't worry, this wasn't done on the 850. This was done back in Cardiff on the 400 megahertz. We did not spend 45 hours getting nothing on a very, well, it was a moderately expensive spectrometer, but not as expensive as the 850. So what do we see? At 12 kilohertz, we did 5 repetitions, and every time it crystallized within 3 hours. And in fact, there was only one case where it took more than an hour. One crystallized almost straight away, number 4 then. We did a single experiment at 10 kilohertz, no crystallization after 17 hours. We got bored at that point. There's the 7.5 kilohertz experiment that I showed you earlier on, crystallizing at about 8.5 hours. But we repeated that, same sample every time, ran for a day, no crystallization. At 3 kilohertz, we ran for 17 hours, nothing. And then we thought, no, we've got to do this properly. We ran over the weekend then, up to about 45 hours, nothing. No crystallization at all across that whole time period. So clearly, spinning is having a significant effect. It's reasonable to assume that if we did this 10 kilohertz experiment a few more times, it would crystallize at some point. But as I say, crystallization is a stochastic process, so you're always going to be looking at somewhat random results, as the 12 kilohertz data shows. So how can we rationalize this? Well, what we can do is we can look at how much of the sample goes into the crystals by looking at the intensity of the signal in the liquid state. Remember, we're only measuring the liquid state. We're not measuring the solid state. And what we find is that the black line here, or the black crosses, I should say, at 7.5 kilohertz, the amount of signal that's left after crystallization is significantly more than the amount that's left in the various different runs at 12.5 kilohertz. In other words, the solubility is different. The solubility is higher at 7.5 kilohertz because we've still got more in solution here than we do at 12 kilohertz. And that's, we think, the crucial factor. Because with a higher solubility at 7.5 kilohertz, that means that the supersaturation, so it's the difference between the solution here, where it's been cooled but is yet to crystallize, and the solution after it's crystallized, that difference is bigger at 7 kilohertz, at 12 kilohertz than it is at 7.5 kilohertz. And the degree of supersaturation has long been recognized as one of the key factors in driving nucleation. And in this particular crystallization, once it starts to nucleate, the whole thing goes literally within seconds. So it looks like the degree of supersaturation is higher at the higher spinning speed, and that's what's driving the faster crystallization. The chemical shifts also change by a greater degree at 12 kilohertz. So that's telling you that there's more of a difference between the solution before and after crystallization when you've got that higher MAS frequency. So it's all very recently, we've just published a very nice paper with Sharon's group looking at the ADOR process. So please do have a look at those as well. All of this work was done with my colleagues at Cardiff, and as everyone else, thanks to both Trent and Dina for all the help that they gave us over the years. And thank you.